Hello dear friends, welcome to the lectures on abstract algebra. From this lecture we shall study ring theory. Earlier we have studied group theory. In this lecture we shall study definition of ring theory, some of its basic types and some examples. We have studied group theory and it is advisable to revise it first. So we know that group is a non-empty set G and together with a binary operations associated with that set G and which satisfies certain properties, and these properties we know are closure property, associative property, existence of identity and existence of inverse with respect to this operation which is denoted by dot. Now in ring theory we have again a non-empty set which is generally denoted by R, and together with two operations. Instead of group there is only one operation that is denoted by dot, but for ring we have two operations associated with this non-empty set R, and these operations are denoted by plus and dot, addition and multiplication. Now here is the definition of ring I have written. We shall first understand the definition and then we will see examples of rings. Definition is: a non-empty set denoted by R is said to be a ring if in R there are defined two operations denoted by plus and dot, addition and multiplication respectively, such that for all A, B, C in R, three elements or any three elements we have to consider, the following laws hold. And these are the actually 8 laws we have listed here. These are axioms of group, axioms of ring theory, and the first is first 5 are associated for addition operation. First is closure for addition, that is A plus B belongs to R, and this means for all AB in R we have written here this common condition ABC are in R, and for all AB in R, A plus B is again in R, that is closure property as we know. Then commutative for addition, we know the usual addition is commutative, but here the addition addition associated with ring theory is plus and dot, may be usual or may not be usual addition and multiplication. So but for this operation plus, it must be commutative. Commutative for plus, A plus B is equal to B plus A. Then associative for plus, that is A plus B plus C is equal to A plus in bracket B plus C. That is here A and B are first operated or added, and here B plus C is added and then combined with A. So this is we know associative property for plus. Identity for plus, there exists an element 0 denoted by 0 in R such that A plus 0 is equal to A for all A belongs to R. So such an element 0 is known as identity for plus. And inverse for plus or additive inverse, for all A belongs to R there exists an element negative such that A plus negative A is equal to 0. Then the two elements are said to be inverses of each other. If their addition results identity element, that is 0, then the two elements are additive inverses of each other. So these are the axioms or laws associated with this addition operation plus. Now the next law is closure for dot. Similar to closure for plus, for any two elements A and B, A dot B is again in R, that is closure property. Associative for dot, similar to associative for plus, we have A dot in bracket B dot C is equal to in bracket A dot B dot C. So this is the associative law for multiplication or dot. And now these are the distributive laws which are with respect to dot and plus. We say the dot is distributive over plus. A dot in bracket B plus C is equal to A dot B plus A dot C. This is left distributive law. And because the dot operation is here on left first, and here first B plus C is written and then dot. This is known as right distributive law. B plus C, this is in bracket, dot A is equal to B dot A plus C dot, and which is known as right distributive law. These are the, we know usual multiplication is distributive over addition. So these are the distributive laws. So thus if these laws are satisfied by the elements in R and with respect to the operation plus and dot, then the structure is known as a ring. So and we denote this as R with plus and dot operation forms a ring. Now here we should note that axioms or laws 1 to 5 states that R with respect to plus operation, these are for plus operation or composition, is abelian group. This is abelian group with respect to addition. And so the non-empty set R must be an abelian group with respect to addition operation. So in group theory we have studied these what is the abelian group. These are the 5 necessary laws to be satisfied by this plus operation, then it becomes abelian group under plus. And then the next are closure for dot. Closure and associative law must hold for dot operation or multiplication operation, and the distributive laws must hold. So then if all these laws holds, then we say R is a ring with respect to these two operations plus and dot. Now next, if you have the an element 1, the property is 1 dot A is equal to A dot 1 is equal to A, then that element is unit element with respect to multiplication. So we write that as ring with unity. In a ring R, if there exists an element 1 such that A dot 1 is equal to 1 dot A is equal to A for all A belongs to R, then 1 is called as unit element with respect to multiplication. We know your usual multiplication, 1 is the identity element, and that element is known as unit element, and the ring is known as ring with unity. Then 1 is the unit element. Of the ring, and the ring is said to be ring with unity. And one more ring that we shall consider in basic type, that is commutative ring. So and that commutative property is with respect to multiplication. Now you see identity, this is identity with respect to multiplication, or which is known as unit element with respect to multiplication. And unit element or identity for plus, that is 0 element. 0 element must be necessary for a ring structure, but unit element is not necessary for ring structure. It is additional property. If a ring has this element 1, having the property A dot 1 is equal to 1 dot A is equal to A for all A, then we say that the ring is with unit element. and if it may exist or may not exist in the ring. If it exists, we say it is a ring with unity. And similarly, commutative ring. Commutative ring, if for all, if R is a ring, and A dot B is equal to B dot A, or all AB belongs to R, then we say R is a commutative ring. So these are two basic properties of or types of ring with unity and commutative ring. And we have defined what is a ring structure. The 8 laws are necessary for existence of ring structure, and these are additional. Ring with unity. If unity element may exist, may not exist in ring. If it exists, then we say it is a ring with unity. And commutative property for dot is also not necessary for ring structure. So if it exists, if the property holds commutative for multiplication, A dot B is equal to B dot A, and then we say the ring is commutative. Addition is commutative, compulsory or necessarily commutative addition. And here identity for addition is also necessary. But these are additional properties for a ring. So this is about the definition of ring, and then ring with unity and commutative ring. Now we shall see some examples of ring. The first and simplest example of a ring is consisting of single element 0. See. First example, if R is equal to, or let R is single element 0 with addition plus and dot defined by, or this can be considered as usual addition and multiplication defined as or defined by 0 plus 0. There is a single element 0 and its operation with itself is equal to 0, and 0 dot 0 is equal to 0. So these are the two operations and single element. So it is 0 plus 0 is equal to 0 and 0 dot 0 is equal to 0. Then this forms a ring because all these properties are satisfied. These properties are satisfied by this ring, by this set, singleton set 0. Then R is a ring. R is a ring known as zero ring or null ring. You see, closure property is satisfied. 0 plus 0 is 0, and that is belongs to R. And commutativity obviously hold the associativity holds, identity is the same, and inverse of 0 is again with respect to plus is 0. Closure property holds, this says, and associative, usual multiplication is always associative. Distributive law holds also. 0 dot 0 plus 0 is again 0 dot 0 plus 0 dot 0, etc. So all these properties, 8 properties holds, and therefore this is a ring. Now what about this, whether it is a ring with unity? No, because unit element is not there, 1 is not there in this ring, and therefore this is a ring without unity. Whether it is a commutative ring? Yes, it is a commutative ring because 0 dot 0 is equal to 0. And thus it is an example of commutative ring. Now second example we shall see as let R be set of integers. Or let R be the set of integers. Set of all integers. Set of all integers, positive, negative, including 0 and also 0. Then that is a ring. So I shall write here. So we have it is unit element and commutative element. These are simple to understand. So these 8 properties are compulsory, and I shall keep these, and then second example we will continue here. See, R be set of all integers. Then I shall write here. Then what about this set of integers with usual addition and multiplication, usual plus and dot, usual addition and multiplication. Then this forms a ring, because usual addition is addition of 2 integers is again an integer, and addition of integers or usual addition is always commutative. It is always associative, and identity for plus is 0. 0 is an integer, so this holds. Inverse for addition. So we know if a is an integer and it belongs to I, or we may say consider the set of integers I, then negative of a is also an integer, and therefore the additive inverse exists. Inverse for plus exists, and their addition is identity element 0. Closure for multiplication. Multiplication of integers is closed because multiplication of 2 integers is again an integer, and therefore this law holds. Associative. Usual multiplication is associative, and therefore multiplication of integer is also associative, and we know that usual multiplication is distributive over addition. This law holds. Similarly, which is known as left distributive law, and dot is on left side, here dot is on right side, so it is right distributive law, and the usual multiplication is also distributive, or right distributive law holds, both law holds, and therefore then R is then this set of all integers. The set of all integers is a ring. Now what about additional properties? Additional properties we have whether it is a ring with unity. Yes, because 1 belongs to this integer. 1 is an integer, and therefore it is a ring with unity. And whether it is commutative. Commutative for multiplication. Multiplication, usual multiplication is commutative, and therefore this is an example of ring with unity, and commutative ring is a commutative ring, or we can write like this, is a commutative ring. Commutative ring with unity. So this is our simple example. This is trivial example. This is a non-trivial simple example. Set of all integers forms a commutative ring with unity under usual addition and multiplication. Now third example we shall consider as the set of even integers. All even integers. That means here R will be of this type. Even integers. 0 is even. 0 plus or minus 2 plus or minus 4 plus or minus 6, etc. So these are the set of all even integers. Set of all integers here we have, we may denote it by I or R. Here is R is I, and 0 plus minus 1 plus minus 2 plus minus 3, etc. All integers, and even integers are 0 plus minus 2, etc. That is divisible by 2. So whether this forms a ring or not. and we may see all these properties holds. So for closure for plus, how to check this property? Whether the sum of two even integers is again an even integer, and it holds. Yes, sum of two even integers is an even integer, and therefore the closure property holds. Commutative for plus, as a set of all even integers with usual plus and dot. So these operations must be specified. We have to define three things: the set, then the two binary operations plus and dot. Here it is usual addition, usual multiplication for the set of even integers. And now we have to check these properties. So it is commutative. Usual addition is commutative. It is also associative, and identity for plus, there is 0. 0 is even. So this element exists. And inverse for plus. Now see, we have listed all even integers, positive and negative together. So plus 2 minus 2 is also there. So these are inverses of each other, plus minus. And inverse exists for addition. Closure for dot. Product of two even integer is again an even integer, so therefore this closure property satisfied. Associative, product, usual product is associative, and also usual product is distributive over addition. So therefore this also is a ring. Even integer, set of all even integers with plus and dot forms a ring. And whether it is a ring with unity, now we can see there is no element 1 here, and therefore this is ring without unity. And next additional property is commutative. Whether it is commutative, dot means product is commutative, and therefore usual product is commutative, and therefore it is commutative but without unity. So then R is, it is a ring. It is a ring, or commutative ring without unity. So above example is commutative ring with unity, and this is commutative ring without unity. Because here the unity element is there, plus 1 is there, and thus we have differentiated the example where ring with unity and ring without unity. Continue in our next lecture. Thank you for watching this lecture.